Welcome back to Integral Calculus. In this video, I want to talk about integration by table. At first glance, this sounds like it is the easiest method of integration that is at all possible. In integration by table, we turn to a table of integrals and we try to find a match for our particular integrand, and then we just copy the solution from the table. So for example, if I have an integral that was something like the square root of x times 2x plus 3, then I would say that a is 2 and b is 3. I would plug them into this formula, and I would plug them into this formula to get my result. That's all there is to it. Of course, one of the big issues with a table of integrals is that they have to balance between having enough integrals to be useful and having few enough integrals that you can actually search through them. So one of the common features of integral tables is headers. So we're looking here at basic forms, integrals of rational functions. If I scroll down a little bit here, you'll see that there's a header for integrals with roots. We've also got integrals with exponentials, and this continues on to a second page where we have some trigonometric functions, and so on, and so on. So this particular integration table that I chose to share because it is available for free online has 121 separate integrals on it. And for a lot of purposes, it's useful, but not for all of them. So let's jump back over to my notebook for a bit here, and let's take a look at a particular example. So how about the integral of the natural log of 9 plus x squared? Right? This is involving natural logs, and I kind of sort of know that there's a formula for natural logs. It's not one that is on the standard table. Why do I keep going there? Sorry about that. That's where we wanted to go, where you could see me. Right. This integral is not on the standard tables, but we saw that we could use integration by parts in order to evaluate an integral involving natural log, but the stuff inside the natural log is kind of messy in this case, so getting that to work is going to be a little bit more challenging than it might be otherwise. Right. So that makes it a good candidate for turning to my table of integrals. I do see that there is a heading that says integrals with logarithms, and if I look through that a little bit, I see here number 45, the integral of x squared plus a squared dx. So I'm going to go back to my problem, and I'm going to write down equation 45. So this table, one of the things I notice is that it's writing tangent to the negative first instead of arctangent. The other issue with this table that we have to pay close attention to is that it does not include plus a constant of integration, which might be important and is important for us in this case. But other than that, since I have addition going on here, it doesn't matter the order. So I just need to notice that a squared is 9, which means that a itself is 3. And then I can plug in, and that's my solution. The result of this integral is x times the natural log of x squared plus 9 plus 2 times a, 2 times 3 is 6. And I'll write it as arctangent because that's what we're accustomed to. And it's x over a, but a is 3 in this case, minus 2x plus c. All right, that seems simple enough, I guess. Let's take a look at another example. All right, how about the integral of sine squared of 4x times cosine squared of 4x dx? All right, so going back to my table, I'm looking at integrals with trigonometric functions. And there are several on the table, so I have to scroll down for a little while. But I eventually start seeing some exponents, which makes me excited. And then here we are. Sine squared of ax times cosine squared of ax. And in this case, our a is going to be 4. That's equation 77. Right, so I'll copy down that formula. And again, in this case, it's fairly straightforward. I just have to recognize that a is 4, and it is a direct matching game. As I'm writing out my solution here, it's going to turn out as x over 8 minus sine 4 times 4 is 16x over 32 times 4, which is 128. And then the table that I'm using does not have a plus c, so I will add that plus c on my own. This one, again, probably we could have figured out using other tools, right? This is sine and cosine raised to various powers. We know how to deal with trigonometric integrals of that sort. This one is not really different, but now that we have this tool at our disposal, we can kind of default to it, right? Really, a table of integrals is someone using all of the tricks that we've been building up all semester and looking at, well, I keep coming up with integrals that look like this, so it would be nice if I had a reference instead of having to redo it every time. And so we have that reference now, we can use it. Sometimes when it works. But as I said, it's not always straightforward. So one more example here. How about the integral e to the 3x over the square root of 16 minus e to the 2x dx? When I look at this integral, I am quickly seeing that I have exponentials. So the first place I'm going to look is my integrals with exponentials listing, which has quite a few entries, but not really anything that looks like what we have. So this is not going to be as easy as the last couple. Just like any other attempts we've had at integration, if at first glance it doesn't seem to work, we try to do something to change the integral a little bit. And kind of our first choice is to try some sort of a u substitution. I saw when I looked at the section marked integrals involving exponentials that there was really nothing there. So what if I didn't have exponentials? What if I had something else? Let's let u equal e to the x. Then du is e to the x dx, and we can do some creative rearrangement. Actually, let's do this all at once. E to the 3x is the same thing as e to the x cubed. And if I split that out and think about e to the x squared and an extra e to the x, and then similarly, inside the radical in the denominator, e to the 2x is e to the x squared. Why did I do it like this? Well, because now I have my du right there, and I've got a couple of things that I can replace with dx. And so all of a sudden, this integral has turned into u squared du over the square root of 16 minus u squared. I am no longer dealing with anything involving exponentials. This still isn't an easy integral, but at least it's not exponentials. All right, now I'll jump one more time to my table of integrals, and now that I have a radical here, I'm going to start thinking about the integrals with roots. There are an awful lot of them on the list, and I don't want to put my head in the way because I think it will actually block the one we need here. Actually, no, I've set this up just right so that it won't. There it is, number 36. So you have to go all the way down this column, all the way up the next one. But here we have x squared over the square root of x squared plus or minus a squared. And that's pretty close to what we have here. Okay, and from there, we've got u instead of x. We've got 16 instead of a squared. So if 16 is equal to a squared, that means that 4 is the value of a. And we can start plugging in. We're going to have 1/2 the square root of 16 minus u squared. And then since we used minus there, the minus or plus, we'll use plus 1/2 a squared. 16 over 2 is 8 times the natural log of the absolute value of x minus the square root of 16 minus u squared. And I'm sorry, that should have been a u, not an x here. That's okay. And then from here, we bring back the plus c. I'm sorry. We remember to include the plus c that they don't have on the table. And then we bring back u was e to the x. So 1/2 square root of 16 minus e to the 2x plus 8 times the natural log of the absolute value of e to the x minus the square root of 16 minus e to the 2x, all plus c. So using a table of integrals greatly expands and speeds up the process of evaluating integrals, but it's not as easy as it seems at first glance. Right? Rearranging your integrand using u substitutions to make the integral you're trying to solve look like something that's on the table can be more challenging than you would think at first glance. On the other hand, sometimes you're lucky and sometimes you're able to find something that very closely matches the form you need. All right, let's wrap up with one for you to try. How about the integral of e to the 2x times the sine of 3x dx? Right. Take a couple of minutes, see what you can do with that one, and I'll see you in the next video.